Hello, and thanks for using TickBoom. In this video, I'm going to work through this question 16a, which was sent through to me by a student. It's a little different to normal because most of the time when a student sends me a question, it's because they're struggling with some part of it, and so they need a bit of extra guidance to kind of work out how to crack the question. In this case, the student actually didn't need any help with this question. They just thought it was so well written and such an interesting question that they thought, why not share it with me so that I could work through it and then share it with others. So hopefully as I work through this, you also find it interesting and hopefully you can appreciate that it's well written. I think it is. In terms of what it is, the question says to define the following sum: Sn equals root 1 plus root 2 plus root 3 plus all the way up to root n. And then part 1 says, by considering the area under the curve y is equal to root x between x is equal to 0 and x is equal to n, show that s minus root n is less than 2n root n on 3, which is less than s. And then part 2 says, hence show that 2n root n on 3 is less than s, which is less than 2n plus 3 root n on 3. Alright, so we're given in this question this sum, Sn equals root 1 plus root 2 plus root 3 and so on, all the way up to root n. And part 1 of this question wants us to show an inequality. The inequality being that s, the sum, minus root n, is less than 2n root n on 3, which itself is less than s, the total sum. And we're told to consider the curve of y equals root x. So I think a natural place to start would be to draw up that curve. So I'll just get a chart happening here. So we'll just get our axes set up. So we'll have 1, 2, 3, 4, and we'll go all the way up to n. So I'll put in n minus 1 there. And we're told to draw the curve y is equal to root x. If you kind of squared both sides, you'd see that x is equal to y squared. So it's kind of like a parabola but sideways because we're kind of rotating our axes. So I know that if we're only taking the positive root of x, the curve will look something like this. And basically we want to consider the area under this curve to help us get to this inequality. And I think whenever you see questions like this, where you've got inequalities and the area under a curve, you can go back to almost the first principles of integration, because we know as we learn calculus and integration that the area under a curve can be given by its integral between 2 points. And hopefully as you were having that introduced to you, you would have learned, or it would have been almost proved to you by taking rectangles and making those rectangles thinner and thinner. So often when you've got some function and you want to create a inequality out of it, you can think about the rectangles around that curve. So what I'll do is maybe in a different color, I'll just draw up vertical lines up to the curve. And there's two sets of rectangles we can draw. The first set, I'll draw the rectangles that form underneath the curve. So these black rectangles here, we know that the area under those rectangles, you can see just visually, will be less than the area under the curve, because the curve always sits above those rectangles. I'll just use another color. If I then draw another set of rectangles, the set that kind of lies above the curve, just draw all of these. So if we look at the area under these red rectangles, we can see that that area would be greater than the area under the curve because those rectangles are always sitting above the curve. So what we could say is that the area of the black rectangles is less than the area of the curve, which is less than the area of the red rectangles. So once we've kind of got that basic starting point with our inequality, we can just evaluate each of these things and hope that it then lets us get to the inequality. So if I start with the black rectangles, the area of the black rectangles would be equal to, so they all have a width of 1, so it's all going to be 1 times something. This first one, the height is the square root of 1, so it's 1 times the square root of 1 plus 1 times the square root of 2 plus 1 times the square root of 3, and so on, up to the last rectangle, which has a height of n minus 1, so 1 times the square root of n minus 1. So hopefully you can see this will just be root 1 plus root 2 plus root 3, all the way up to root n minus 1, which is kind of this part of s, but not including the Sn. Oh, sorry, not including the square root of n. So if I moved the square root of n over, then that is what this would be. So I could write that as s minus the square root of n. That's the area under the black rectangles, and it's a good sign because that's the first part of our inequality. Now if I think about the area under the curve, that's going to be given by our integral between 0 and n of y is equal to root x. So I'll just write that as x to the half dx. So in terms of integrating that, we will add 1 to the exponent and then divide by the new exponent. So that would be x to the half plus 1, 1.5, or 3 on 2, divided by 3 on 2, between 0 and n. So I'll just bring this out. So 3 on 2 in the denominator, we can invert it. So it will be 2 on 3 times n to the 3 on 2 minus 0. So that's going to be 2 on 3 times, we could write this 3 on n to the 3 on 2 as the square root of n cubed. And given I'm running out of space, I might just keep going this way. So that will be 2 on 3 times the square root of n squared times n, which would be 2 on 3 times the square root of n squared is just n, and then there'll be a root n left. So that is pretty much this here, 2n root n on 3, 2n root n all on 3. So I'll just write that, 2n root n on 3. So that's a good sign because that's the middle part of our inequality. So now we just need the last part, so I'll definitely have to turn over for this. The area of the red rectangles will be equal to, so they'll all also have a width of 1, but this time we're starting from the one with the height over root 1, so 1 times root 1 plus 1 times root 2 plus 1 times root 3, and so on. But this time we do get all the way up to root n. So we don't stop at root n minus 1, we actually, the last rectangle has a height of root n. So 1 times root n. So that's just going to be root 1 plus root 2 plus root 3 all the way up to root n, which is our sum. So we can write that as s. So now if we bring that all together, what we can conclude is that s minus root n is less than 2n root n on 3, which is less than s. And that's what we were asked to show, so as required. Alright, now part 2 wants us to hence show that 2n root n on 3 is less than s, which is less than 2n plus 3 root n on 3. Now whenever you see a hence in a question, that's kind of the question writer guiding you to say, maybe try thinking about what you just showed. We can see what we're trying to show here in part 2. A lot of those components are up here already, especially this 2n root n on 3. And there's an s there too. Actually, this part here, we can take directly from part 1. So really, it's just about thinking about this part here, which given we're told, you know, think about what you just showed, maybe it's simply a rearrangement of this. So let's start with that. So what we can say is if s minus root n is less than 2n root n on 3, then I can just bring the root n over. So s would be less than root n plus 2n root n on 3. If I give that a common denominator, that will be 3 root n plus 2n root n on 3. And then just simplifying that, we've got a common factor of root n. So we'll have 3 plus 2n, but I'll just write that as 2n plus 3, since that's the way the question has it, on times root n, all divided by 3. Which is this part here. So therefore, if I combine what we know, so what we know from part 1 and what we've just determined through rearranging, we can say that s is greater than 2n root n on 3. So 2n root n on 3 is less than s, which itself is less than 2n plus 3 root n on 3 as required. So part 2 is fairly simple. I think it's the kind of part of a question that sometimes I think question writers put this in so that if you totally stuff up part 1 and you just can't work it out, you can at least go, well, maybe I can grab a mark in part 2 here, because that word hence lets me know I can make use of what I showed in part 1. Even if I couldn't show it, I'm still told it. So you can kind of pick up that easy mark through a very simple rearranging. But clearly the bulk of the marks related to part 1, and you can see why it involved more thinking and more work. But it really is this part 1 that I think the student who sent this through to me, this is the bit that's interesting. It's a technique that's helped us with this question, but it's actually, you can almost generalize it and almost with any function you can think of that's easy enough to integrate, you can come up with inequalities just by thinking about the rectangles that will sit above or below whatever curve you're thinking about. So it's definitely a tool to add into your toolkit, your mathematical toolkit. I have seen other questions pop up in harder 4-unit or Extension 2 math exams that require this technique. Actually, one of the hardest questions I've had sent through to me since starting Tick Boom involved essentially this technique. So it's definitely a good one to be familiar with, because you never know, you may end up sitting an exam that requires it. But even beyond exams and just thinking about mathematics more purely, this technique is a great one for coming up with inequalities that may prove useful in whatever context. So hopefully you have found this question interesting, and thank you to that student who sent through the question. Yeah, it definitely is an interesting one, so I'm glad to have been able to work through it. And tick boom.